8.7 notes, modeling with exponential and power functions. All right, what we're really doing today is just combining functions. So this should be real quick. There's really not any homework for this, but I do have one problem at the end for you to do. All right, so first thing we're going to do is we're going to combine a linear function with a constant function by addition. So it's just really adding two functions. So we're going to create h of x by doing f of x plus g of x. All right, f of x is 4. G of x is 3x minus 2. We combine our like terms, and we get 3x plus 2. All right, so that's our new function, h of x. All right, next, we're going to combine a quadratic function with a linear function by addition. Okay, so we're going to create new function g of x by adding f of x and r of x. So g of x equals f of x plus r of x. So g of x equals f of x, which is negative 3x squared plus 2x minus 5 plus r of x, which is negative 3x minus 6. All right, so again, we're going to do this, since it's addition, all we got to do is combine like terms. Well, we only have one x squared term, so we just bring it down. Now we have a positive 2x and a negative 3x, gives us a negative 1x. And then we have a negative 5 and a negative 6, which gives us negative 11. So we get our new function, g of x equals negative 3x squared minus 1x minus 11. All right, and example 3. We're going to combine an exponential decay function with a constant function by addition. So again, we're going to do p of x this time. And we're going to get p of x by doing m of x plus n of x. All right. So now this looks like m of x is 2 times 1/2 to the x power plus 8. And that is actually our answer. Because we can't combine any like terms. So we would just leave it like that. All right. All right, so it's just really building functions. Well, really what I want you to be able to do is this. All right, this is how you use this stuff in real life. So we're going to combine functions in real life. So we got humans have a constant body temperature of 98.6. When a person dies, the body starts to cool exponentially. All right. Now, the cooling formula looks like this. This is what the cooling formula looks like. Okay. So we have the temperature at any point in time is equal to r of x plus b of x minus r of x, and that's in parentheses, times e to the negative kt power. All right, so r of x happens to be the room temperature. B of x happens to be the body temperature. K, when that formula, is a constant, and it is equal to a negative 0.223, and the t is the time in hours. All right, so we're going to use the information and we're going to write a model for a room temperature of 60 degrees. Okay, so here's our model. So we got T sub T equals R of X, which is our room temperature, we said is 60 degrees, plus parentheses B of X, which is the body temperature, so that's 98.6, minus R of X, which is the room temperature, all right, times e to the negative 0.223 T. All right. So now we got T of T equals 60 plus, and you can do this. Anytime there's something in the problem you can do to simplify it, you need to do that. All right. So 98.6 minus 60 is 38.6 e to the 0.223 t. All right, so that would be our formula. Now, what you're going to do is you're actually going to use this formula. And you are going to do this next problem on your own. And then you can send me your answer. What I'm going to do is the person who gets closest will get bonus points to the actual time. Now, remember, they are looking for the time. So you have to give them a time. And the more accurate the time is, the more chance you have of actually getting this question right. And that's it for today.